Welcome back, everyone. This is a video that is replying to Etho's latest Let's Play Mastermind with some potential changes he can make to fix up a few errors where people were talking about in the comments how you get an incorrect number of white powder. And also, he asked if there was a nice way of displaying the results of each guess. So, I've got something nice here for that. So, first, this is going to be just a first video in the tutorial. I'm probably going to try to clean it up and make it nice, but right now I've just been playing around. So first right here, this is my idea for how we would display the results. You can just place concrete powder like so, and what happens is these pistons all push out and they'll all fall in a nice line. So right now I haven't set up here, you'd want, this is a 4 o'clock, you'd want a single pulse of a 4 o'clock to get this to work properly. Right now I just placed a repeater, but that wouldn't be too hard to fix up. Here we go. On, off, on, off, on, off, on, off. Push out, and now push itself back in. The length of the repeaters here is extremely important. If any one of these is messed up, it won't work. So if you want to copy this, you should probably just take some screenshots or pause my video. Basically, the pulse comes in here. It powers each piston when they get to the correct spot like this with some delay. The wire does pass underneath all of this because some of the pistons are powered multiple times on their way back. So we've got one fully extended repeater here. It comes up in the middle, and on the other side we have one short delay repeater, just like that. We've got all these other wires. You just copy the exact lengths that you can see here in these pictures, then you will get it to work properly. Additionally, there's a couple other important features. These two half slabs are very important because, as you can see, if we just put some power real quick, if I put power, well, let me just put power right here. You can see it powers up. This redstone wire powers these up, but it does not work the other way. Redstone power can only go up half slabs, not down. So if I power this, for instance, it does power that eventually because it makes a big loop, but you'll notice it's not immediate. Let's wait till this goes away. So it powers up, and it did not power that one immediately. So they're very important so that power does not go back down this and create an infinite loop, powering everything up forever. Let me quickly fix this up. When you mess with it, it messes with the results of everything. So on, off, on, off, on, off. You get a button maybe that somehow you turned into giving you a 4-tick pulse. But right now, this is just what I'm doing. So the results, as you can see, is that it puts them down like so. So if I just put some random line or whatever we end up having here, when I get this setup going, they all push off and they all fall. So that could be used nicely to display the results of the game. My bad, the recording cut out there, had some issues. But basically, when these push over these layers like this, we can get something like this. So let's assume that this right here is the answer. So the first attempt that I'm going to play, I'm just going to build this out again. The first guess was, let's say, yellow, red, orange, yellow, red, orange, yellow, and maybe the game puts the sand blocks on the side just so it looks nice. The result is this, that we got one right, the orange. We got one white result because we have a red and there is a red, but it's in the wrong spot. So the result that would get pushed down would be this. Now, basically, what would happen is we would have played this row, some set of pistons would have pushed the guess forward, and then we would, this row would fall in, and then a set of pistons that would be over here would push all this forward. So when we made our next guess, which we can say is green, purple, orange, red, that would fall down here, it would get pushed forward, and then our results would get given to us of black, black, white, orange, orange. Now, one possible problem with this is that there's a limit of how far pistons can push, but what you could do is just have this be like 11 blocks long, fall down one, and have another set of pistons that continue to push, and they just be on slightly different layers. But basically, you just have a bunch of these sitting like right here. And they would just extend every round, pushing it forward, allowing you for the next layer to fall in via some form of this. Now, for this to work, you need some system that can figure out what box to place. So we need a placer, which is somewhat difficult to make, but it doesn't involve that much complication. Basically, you can have some form of system similar to this with blocks higher, where you have the different, basically I could get some hard block here, down at the bottom. Just picked ice because I have it. Let me set it today, weather clear. And we have various sands on top. And then there'd be a whole stack of them. You probably have it on two sides. And then whichever sand ends up getting picked, which you can determine via some redstone signal, then that piston will extend and knock that particular piece of sand down into our trap over here in front of these pistons, and then the pistons can push them in. So, for instance, maybe it's orange. This didn't work properly. I haven't thought it through. But basically, you want this one to be a sticky piston, and it would pull this block back. And then this would all fall down appropriately. You might have some issues where you don't know what block's what, but what you probably end up doing is having stacks of one block. I don't know exactly, but this is how you could potentially put the blocks in here and then push them out accordingly into these rows. So this system works pretty nicely for demonstrating your results, but there's still the question in the error we had earlier where there were too many whites being picked. So for instance, if you guessed blue, 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 and the answer was blue, purple, yellow, purple, yellow, or green, this would give you, in the current system in Etho's episode, a black because this one's right, and then give you a white because there is a blue in here and a white and a white, which isn't true. You want to somehow say, okay, this blue's taken, so these blues don't count because this blue's already used. So over here, I've been playing around a little bit with using hoppers to determine stuff. So one thing you can notice is that water streams going over hoppers. It does work. So if I put this in, it's going to fly all the way to the end, so it's fine. The ice on the sides and the speed it gets over here is enough. But one problem if you just have a normal stream is that items can get stuck in the hoppers even when they're not falling in. Let's see if I can get one. Yeah, right there. Because hoppers have a little, you can fall down in them a little bit, and items do that. So you need to have this sideways stream here so that the items rest along the side. That way they push along the edges of the hoppers and they don't fall in. So in here I just have set up items of each. So the items will only be able to go into one specific hopper. And so the green one will sink in over here, and you could do something with a comparator such that when a single item enters these hoppers, it sets out a redstone signal. And that way you could figure out what items were dispensed, and as a result, using some system like this, push out the appropriate block and actually be able to display what the final result of the game is. Additionally, if you want to be extra complicated, you could have 24 of these hoppers. You could have 6 for each color and for each block, and that way, if, for instance, this was the result, blue, purple, purple, green, if you locked the hoppers after they an item went into them, so the comparator determines, oh, an item went in, we're going to lock the hopper now, then the blue one would go in here, the purple one would fall in here, and then the second purple one would have to go to the second set of 6. So then you could tell which, the order of the output blocks and how many there are. And using redstone logic, I'm sure you could then figure out some way of determining the white concrete powder successfully. Over here is something that will probably help with that. I did not make this compact at all. I set up really quickly, but basically the idea is that I'm using 2 RS NOR latches in order to represent bits. So an RS NOR latch, we'll just build another one quickly over here, basically works like this. So you put one torch here, redstone wire. So let's say that this wire right here is the current state of the system. So if I turn this on, when I turn it off, did I do this backwards? I think I did. So, well, when I turn this one on, no, oh, there we go. That is my problem. Okay, so this is on right now, and when I turn this on, nothing happens. It stays on. When I hit this wire, it turns off, and then it stays off no matter what I do. And this one always turns it on. So basically, you can send in a signal to turn on and send in a different signal to turn it off. Here what I have is two of these stacked on top of each other. So I've got one down here, one up here, which can represent four data values, 0, 1, 2, and 3, which is perfect because we can have up to 4 of each color in the final result. You could have 4 blues. So if when you're trying to calculate whites, what you might want to do is figure out how many of each color there are, regardless of their position, because the position doesn't matter too much when you're considering the white concrete powder. So if you did use the system over here with 24 hoppers, 6 of each color for each position, you could basically make a counter like so. So what I have here, let me just demonstrate how it works. Right here, this wire, right here, and this wire are the outputs. In fact, I'll put some pistons up here. Let me just make sure this turns on. Yeah, to demonstrate them. So both right now they're both off, so we're in state 0. So if I send a pulse of adding 1, the bottom one will not go up because I put it in the wrong spot. Hold up. But now this wire's on, so now it goes up. That's 1. When I turn it on again, then we go to 2. When I turn it on again, we get 3. When I turn it on again, we go back to 0. This is not actually that complicated. It's basically the way it works. We have a bunch of T flip-flops. T flip-flops are pretty simple to build. You just do something like this. Put some regular pistons like so, and just power this top in some way. You got to put torch here, torch here. So the idea is that when I power this, and whenever I unpower it, it switches positions. So you could have like a torch down here and redstone wire, and so whenever it goes on that one particular side or the other, the redstone wire is going to turn on because there's a block or not. What I've done over here is instead I've used a redstone block, which eliminates the need for this. So I basically, it's the same thing, but the redstone block is close enough to this wire, it will power it. I need to put this back. There we go. So let's just assume basically this is our input of, we got a block that is of a certain type, like purple for instance, and it goes to both this this T flip-flop and this T flip-flop. So this one basically just switches the input to this RS NOR latch, and so half the time it's on and half the time it's not, whereas this one is turning it off and they're offset. So every other time this one turns it on, says turn this output on, and the next time that this torch turns off, this one says turn it off. We can make this probably a little easier with a button as well. Just some form of pulse. So that this T flip-flop moves, now it's powering this to say turn the bottom one on, and this T flip-flop also moves, which powers the inverse, which says turn this bit off. Now we have to worry about the second bit, so we're in state 0 right now. Let's go to state 1. So when this one turns off, we want this one to turn back on. So we have another T flip-flop right here that will power and turn this one on every other time, because when this only moves when this turns off. So when this turns off half as frequently as this does, because half the time this turns it on, half the time this turns it off. So when this turns off, half the time it's going to power this and turn this on, and the next time it turns off, it's going to stop powering this. And we're just going to deal with the other side by extending this wire over here, having another T flip-flop, and having it work the other half the time. So right now, let's go back to 0. So we're at 0. This one's off, this one's off. This T flip-flop is not powering up here to turn this on, but this T flip-flop is powering to turn it off, which is great. So when we flip this, first time, this is going to turn on, so nothing's going to happen here. This one's going to turn on, nothing's going to happen here. So nothing's going to move on the top, but the bottom T flip-flops move every time I hit the button, so they're going to flip this to the on state. Now, when we turn this off, this wire and this wire are both on now. They will always be the same because when this one turns on, it turns this one on. So now when I hit the button, both these T flip-flops are going to switch as well as those two. Now this one's off, which is no longer telling this to turn off, and this one's on, which is telling this to turn on. And then the next time nothing happens on the top bit, and then finally it switches the top bit again as well. So you could compact this a lot, but this would be a nice way of representing 2 bits using 2 RS NOR latches and 4 T flip-flops. And that could be used possibly to determine the white concrete powder. Now, this is probably not too applicable to this particular project, but if you did want to do some form of complicated addition, there are ways to make things like full adders. This is a full adder I built. I don't exactly actually remember how it works. There's something complicated over here. I think this is my C in right now. Basically, though, it involves a couple AND gates, a couple XOR gates, and an OR gate. These are XOR gates. So I'm probably going to make a tutorial on full adder at some point. It's pretty useful if you have some form of bit system. I have a pretty complicated one over here, actually, I built some time ago. But so you could do this if you wanted to enumerate things with bits for this project, which would work. It'd just be a little bulky. I believe this is how many bits you would need, 12 right here. If you do it in bits, there are 2 to the 11. 2 to the 11 is more combinations than 6 times 6 times 6 times 6, but you need a 12th bit for negative just in case you want it. I don't know why you would, but you might. But yeah, so I'm going to probably try to build this up and make it look pretty, but I think this right here probably solves Etho's problem of how do you display the results. You just pile them all out, push them forward, and this right here is a way of counting the number of concrete powders of the same type that come through. It would work with this system. Every time another one came through, if you delayed them slightly, it could update a counter, and you'd be able to say 1, 2, 3, 1 of this, 2 of this, 1 of this, and then you could subtract the ones that you know have blacks, and then say, okay, we're going to subtract 1, and now it's 1, 1, 1, and that way you can properly count the white powders.